Okay, so we're going to go over the exam review. Your testing days will vary depending on your periods. Of course, the seniors will be testing first and second period first on Wednesday. So, let's hop right down to it. Hopefully you tried the review on your own the first time and you're using this as a check. If you're doing this just to fill out the review, that doesn't bode well for your performance on the exam. So, first group of stuff is, hi, do you know what you're looking at? This, of course, is the linear parent function. This, of course, is a quadratic. The next one, of course, was an absolute value. The third one, you can tell it's going from 1, 4 up 2, 3 up 9. This is a square root. This one's slightly less than obvious. This is an exponential. In this case, you know it's an exponential because here we went from 1 to 2, we went from 2 to 4, and if we keep going, it'll go from 4 to 8, and so on. This is actually y is equal to 2 to the power of x. This one is a rational function, specifically that y is equal to 1 over x. And this here is the inverse of an exponential, which is a logarithmic. So that's it for that part. Now let's take a look at domains and ranges. The domain is the possible values for x, the range is the possible values for y, so basically how far to the left and how far to the right. Because this is continuous, we will be using inequalities. So we look and we see that this continuous function goes as far left as -6. Upon closer inspection, we find that the point is actually defined at -6, and so we say that -6 is less than or equal to x, and then the furthest to the end is 8. Now, it's kind of hard to see on the camera, but if you look closely, this is an open circle right here. You'd have to see it on the paper to see it as a certainty. And so since the circle is open, that point at 8 is not defined. And so we say that the domain is -6 less than or equal to x less than 8. Because this dot is closed, we have the equal bar. Because this dot is open, we do not. A similar circumstance you'll find in the range. The range is from bottom to top. So the lowest point is an open dot at -7. Is less than y, which the highest point is +8, which again is an open dot. So that's how you do continuous functions. Now, for discrete functions, life is just a little bit more painful. What you do is you tabulate the x values from the left to the right and you delineate them by commas. And so these are arranged as a set rather than an interval. So you start with A and you observe that A is 3 units to the left of the origin, and so we say that's -3. B is 1 unit to the left of the axis, so it's -1. D is 2 to the right, so that's 2. C is 2 further from that, so that makes it 4. And then E is 2 units from that, and that makes 6. The range, you start at the bottom, which is the C point, which is down at -2. B is at +1. D is at +2. A is at +4. And E is at +6. So in other words, you have to plot the individual values and separate them by commas. Do not get discrete and continuous functions confused, because I can guarantee you on the test they'll ask you for a discrete function and the same values as an interval will be given as a distractor. Sorry if my voice is a little raspy, I'm getting over a cold. For this part right here, what you're doing is you're identifying the domain and range based on the transformation of the following based on its parent function. So in this case, this is a square root curve. Now, if you have to visualize it, you shouldn't have to, but if you have to visualize it, you can always graph the bloody thing. So you've got the square root of x plus 5 minus 2. It's a square root curve. It has a vertex here at -5, -2, and it's going up. So when I define the domain, I actually start at -5. As you can see, there is a point at -5 and -2. That's the endpoint. Now, that endpoint is as far to the left as you get to go. So your domain is from -5, which is less than or equal to x, and it keeps going without end. To keep going without end is to be infinite. So we would write it as less than infinity. The other way you could see it appear is just that x is greater than or equal to -5. Both of these statements are logically equivalent to each other. You could see it either one of those ways. The range, in like manner, the least element is -2. The point is defined at -2, and it keeps going to infinity. It's hard to see that it keeps going to infinity, but it does. It keeps going up. It just goes up rather slowly. So again, that is logically equivalent to saying that y is greater than or equal to -2. It is a translation. Insiders lie. So really your vertex point is -5, -2, which means you moved it 5 units to the left and 2 units down. That translation describes the transformation, and in this case there is no reflection. Now let's take a look at the domain range of this next one. This next one is a quadratic. In your quadratic, and let's also take a look at this on the calculator. So we're going to just plug it in. So we have -x minus 3 quantity squared plus 5. I did not do that right. There we go. It is a parabola. Specifically, it is a quadratic. It is a quadratic with a leading coefficient that is negative, and so we know it's going down. Once again, it's in vertex form. Insiders lie. So my vertex is actually +3, +5. It is a reflection because it's going down. I am reflecting across my x-axis. So let's go ahead and put those things in there first. Okay. Transformation, again, that is describing the transformation. Translation, we went 3 to the right, and we went 5 up. Now, the range and the domain. This is going to be a little bit more fun. The domain. Looking at this, and we've got a little bit of glare from the document camera itself. There is no limit to how far to the left or to the right it can go. You can write it as an interval, which is to say that x is between -infinity and +infinity, or you can say that x is all real numbers. Both statements may appear in the multiple choice section of your test. The range, on the other hand, has some limitations. Your vertex has a highest point of 5. That's a vertex. Where x is 3, y is 5. That is the highest point. Every other point must be less than that. So, you would either see it written as y must be less than or equal to 5, because you notice the parabola is actually defined at 5, or you would also see it as negative infinity is less than y is less than or equal to 5. Either one of these might be in the solution. Both of those are logically equivalent statements. There we go. Now, this next one was an exponential. So, going ahead to 3 times 2 to the power of x plus 6. And we graph it. Okay, so we take off relatively quickly. So we go to the table. Values get smaller and smaller and smaller, but you will notice that we never cross 0. So we do have a vertex. X plus 6 describes our horizontal shift. It is a horizontal shift to the left, because insiders lie, and the positive 6 is inside the exponent. So we have negative 6 comma 0 as our reference point. Even though the point doesn't actually get to 0, we're still sliding it 6 to the left. So 6 left is our translation. We have no reflection. Transformation, we already described that. The range and the domain. Let's talk about the domain for a moment. We're starting at negative 6, but in actuality, exponential functions, as we saw on the previous page, they kind of look like this. Which is to say, they have no limit, either on the left or on the right. So the domain, again, is between negative infinity and positive infinity, or, as we said before, all real. All real numbers. The range, on the other hand, does have a limitation. The range is that y has to be greater than 0. But that could also be the same as saying we are going from 0 to infinity. Now, unlike our previous examples, y never actually gets to 0, which is why we do not have the equal bar underneath. Okay. Inverse functions are those where you simply switch the x and y. Inverse functions are written as f inverse of x. Graphically, inverse functions are reflected across the line y is equal to x. If I have two functions that are inverses of one another, let's say I have an exponential and a logarithmic, they should be reflections of one another across the main diagonal. And the main diagonal is the line y is equal to x. You have to know that as a fact. Now, to find inverses algebraically is relatively simple. It is a two-step process. Step 1, switch x and y. Step 2, find the new y. So, let's try it on the ones they gave us. So they started off with y is equal to x plus 5 over 7. You're going to switch your x and y, and you're going to say that x is equal to y plus 5 divided by 7. And now you're going to isolate the new y. Well, the first thing you're going to do is you're going to cancel division by 7. Well, what cancels division by 7? Well, that's multiplication by 7. And what we do to the right, we are algebra to do to the left. So now we have that 7x is equal to y plus 5. In the interest of simplicity, I'm going to use my reflexive property and rewrite this as y plus 5 is equal to 7x. My last step is then to cancel the constant 5 by subtraction. These cancel to 0, and I am left with that y is equal to 7x minus 5, and this is my new inverse function. if I wanted to write it as an inverse function of x, we would write it as such. Okay. Next one is a little bit trickier. I kind of want to do that one third, and because this is my video, I'm going to do that one third. Okay. So let's do the third one, and then we'll get back to the second one. So this, you do the same thing. You write it as x is now equal to 1/2 y squared minus 3. Now, in your standard order of operations, you square, multiply by a coefficient, add or subtract a constant. When you're solving, you have to do the opposite. So the first thing you're going to do is you're going to cancel the constant. So we're going to add 3. So now we have 1/2 of y squared is equal to x plus 3. I hope you noticed I just went on ahead and did the reflection in the next step as well, because I don't like repeating myself. Then, what is the opposite of taking a half? Well, the opposite of taking a half is multiplying by 2. Now, you don't necessarily have to do the distribution. I'm going to just because. So y squared is equal to 2x plus 6. And then the last step is to take the square root of both sides. Now, in actuality, because we started with y squared, there are two solutions. Y is either plus or minus the square root of 2x plus 6. This actually makes two separate functions. And depending on which quadrant you're in, one of them will be the inverse function at hand. Okay, now for the fun one. Y is equal to 2 to the x minus 4. So, once again, say, alright, x is equal to 2 to the y minus 4. First thing you want to do, cancel your constant. So now you got 2 to the y is equal to x plus 4. Now I put myself a space there very conscientiously. What cancels a base of 2? A log of 2. So we are going to put the log 2 of 2y and the log 2 of x plus 4. I know my 2 didn't show up too well on that one. Sorry, I'm writing in pen. So, log 2 cancels base of 2, leaving you with y is equal to the log 2 of x plus 4. And that's it. Remember, the inverse of a function will be another function. Not going to be anything more interesting than that. It's not going to be a value. I asked you to find an inverse, not to evaluate anything. Okay, before I tidy off this, which we'll call video 1, I need to show you how to sketch the inverse of the following little C diagram. Now, the thing I find offensive about this is because this is not actually a function over the entire quadrant. It's a function on a restricted domain, and even then, this would not be a function at all. It fails vertical line test. That being said, we can find the inverse of the relationship, as it were. So the easiest way to do it is to plot the points into a table. So you start with the first one, that's 1, 3. Then you've got 2, 2, and 2, 4. Then you have 1, 2, 3, 4, 5, 1, and 5, 1, 2, 3, 4, 5, and 5, 5. For the inverse function, all you really have to do is switch the x and the y values. And so since the y value here becomes the x value there. And then you just plot it in the new spot. So you go, alright, 1, 2, 3, and 1. 2, 2, 1, 2, 3, 4, 2, 1, 1, 2, 3, 4, 5, and then 5, 5. and that should be the new function. And if you actually melded them together, yes, they would be reflections across the main diagonal. It's not going to be terribly obvious just by shifting them over, because you'll notice that the axes are a little off. But that is how we do it. Okay, stopping video 1 right now. We'll pick up in Unit 3 for the next one.